So what we want to do here is that, just to put things into perspective here, is that we want to go in and look at, right, there's a whole bunch of steps here. Ultimately, you're going to see that we're going to have step 1, which is derive the second order equation. Step 2 here, you're going to have to write out the natural response. And you're going to see that that's really not a trivial thing. There's algebra, there's pieces involved that you'll have to do that. And then you'll see that we go in, and all by itself, we need to determine the initial conditions. And once we determine the initial conditions, then we go in and we apply the initial conditions on the solution. And I think I do these as 2 separate steps. This could be a 2x2 matrix all by itself. There's going to be a different 2x2 matrix right here. So like, this is literally, if you remember the quiz problem that we had in chapter 7, that second question, where we had the second order equation, where we had to calculate the current of the cap and the voltage of the inductor. This is it. That's a problem right there, all by itself. So this is a fairly involved process here. So then we, I think I call this step 4. And then you'll have the solution after this, and then step 5, I believe, is solve the problem. So it's very similar to what we saw before. Okay? Very similar to what we saw in chapter 8 here. Okay. I gotta lube up here real quick. So now, one of the things that I said before here is that the one technique about deriving the differential equations was that you could use the direct method. But it turns out that that method is really inefficient for about 20% of the circuits. It would not work. And I've had numerous people transfer and say, oh my gosh, I'm so happy about the Cramer's method. Now, Cramer's method is really what people call it is the operator method. I probably changed the wording a little bit, but now we're still on step 1, but the method that we're going to go after here is the method I call method 2 here, and we want to do Cramer's operator. And this is far superior than the other technique. Far superior. Now, why is it far superior? Well, one, I'm not allowed to talk about certain types of transforms for differential equations. Like I can't talk about Laplace transforms. I can't talk about like Fourier transforms. That's actually the second part of this course. But technically, those would be better techniques than this, right? But under the circumstances, this is a fairly straightforward method that looks very similar to the direct method, but it's not. But it has really nice, deep implications of what is going on. And so what happens here is that all of the problem-solving techniques are the same. What we do here is that we replace the derivative operator or the integration operator with a variable. And so, for example, so what we're going to do here is that we're going to replace ddt by the operator s hat. Now note, the book does not use s hat. It's what I do. Because if you were to look at the book here, the book continues to use S with the solutions S to the natural response here. So in physics, we use hat for operators. So I continue to do that. And then the integral of dt is then S hat inverse. Right? Which is also, just to remind you, some people forget this, it's also the inverse like this here. This is the only change that you really get in the Cramer's versus the direct method with the derivatives. And this is, like I said, this is a very big change. And the implication here is that you're going to see that there's a certain determinant that really determines what happens here in step 2. So then I go in and I could do so if I change these guys, you could then see here that if I'm talking about IC, which is C dV dt, now it's C S hat dC. And now I just treat S hat as a variable that I could just kind of move around and not really think about it more than that. And you could see that the nice thing about this here is that if we treat S hat as a derivative term, as this operator, no, it's very easy to solve for VC. So if I look at this here, I could then solve for VC. So if I look at how do I solve for VC, well, it's got to be VC, which will then be 1 over C S hat inverse of IC. And as we already know, that the integral of the current is what really gives us the voltage. How much charge is being placed on a capacitor. So the exact same thing happens with the inductor. So if I start with VL, right, it's the derivative of the current to get VL. And if I do the exact same thing here, and I solve for IL, you can see that IL is the inverse. What's kind of tricky about this is that we are moving integrals around, derivatives around. But that's ultimately what the big change is right here. And so now what you're going to see here is that by treating S as a variable, we're going to get an operator matrix. And when we take the determinant of this operator matrix, as you will see, it will give us the second order differential equation. Yes?
Why are we talking about S hat in terms of inverse instead of just putting it in the denominator? Is there a reason for that?
It's the exact same thing.
I know it's the same thing, but whatever.
I can put it there for you.
Okay.
I can do that.
This is great. Thanks.
Just notation. No, I'm not trying to be a smart ass. I'm just saying.
Sure.
So what I can do here is that I could then go in and start to sort of like do an example of how I would do this. So just to very, very, very quickly remind you of this process. I don't think I actually give this to you on the equation sheet. You got to memorize this process. So how about if we write it down very, very quickly and just show you what I'm going to end up doing here is that if I look at this Cramer method, clearly it's an operator. I still have these series of steps. I still replace x1 and x2 where I'm solving for this guy right here. And remember, what's really the key thing about that, identifying that variable x2 is for determining the initial conditions. Right? That's the usefulness of it there. Under normal conditions, I wouldn't even care. But that's why we do that. And then what do we do from here? We use step 1, 2, where we use KVL and KCL and rewrite resistor values into VL, IL, IC, VC. So we got to rewrite those resistor values into that term right there. And then the way I did it before here is I says use VC with this operator and VL. Ooh, I'm messing up here. That's incorrect. So now I convert the terms into derivative terms. Right? And identify equation 2. Okay, that's the key thing right there. And then here's where it really changes. You get to step 4 here, and what you're going to see here is that we want to derive now the second order equation. And when you go derive this, what we do here is that steps 1 through 3 have generated 2 equations and 2 unknowns. Okay? And when you look at this thing here, what you're going to get here is you're going to get something like this. So what happens now is that one gets a system of equations. And for the sake of simplicity, I'll write them in this term right here. So I got x1 and x2, and they're going to have some constants. Let's call them c1 and c2 here. And what we want to do here is that we get a system here. And so if I rewrite the system, it's going to look something like this.
This is still on the path to deriving the differential equation?
Yes. So we get this matrix equation. And this here is what I call the coefficient. It's not the way spell coefficient. Okay. I'm screwed up.
Copy.
Coefficient matrix. And so what you're going to find here is that you get the following thing. You get x1 and x2, which are typically what? The voltage of the current, or the voltage of the capacitor, the current of the inductor. When you do that, what we're then going to do here is that we're going to solve for x1 or x2. And here's where the power of this equation is. You really don't care so much what this is right here, because now you choose what you want to solve for. So let's say that you set up to solve for VC, you really realize that you have to solve for IL. It doesn't matter. You get this matrix term that I could solve for either one of these two. But there's something really, really deep though. This coefficient matrix is the same for variables x1 and x2. Let me say that one more time, because I really want to stress the importance of this thing. This coefficient matrix is the same for variables x1 or x2. In other words, the current of the inductor the voltage of the capacitor, see this same matrix. Because this coefficient of matrix is the same, the current of the inductor and the voltage of the capacitor will have the same natural response. That is the core of it. So there's no choice on what the inductor or the capacitor are going to do. Because this term is the same, they have the same natural response. The direct method gives you no intuition at all. It's, like I said, for calculational wise, this is far superior, but to understand what's happening in the circuit, this is still far superior. So what we do now is that we go in and now we solve for x1. How do we solve for x1? We use Cramer's method here. And the way we use Cramer's method here is we do the following thing here. We take, so what we'll do here is that we've got to take a determinant of a matrix. And this thing here, I'm now going to rewrite as a symbol D here. So now I'm going to take D, and by definition, it's the matrix, it's the determinant of this cofactor pair here. So it's got to be A11, A12, A22, A22, and A21 like that. So that D is actually an operator matrix. And the way we calculate matrices like this, we do what? We sort of like cross here. So as we do this cross, we multiply A1 times A22. And then we subtract as we go the opposite direction, and it becomes A12, A21. So that's how you would take a determinant of a matrix like this. So now, here's what this equation says here. Okay, let me see if you can understand what I'm saying there. So I'm going to write it one way, just to help you understand, and then I'm not going to do that again, because it's not efficient in terms of time. Okay, so now when we solve for x1, here's what we do. We look at this matrix, and remember this column here is with the x1s. This column right here is with the x2s. So what you're seeing here is that I now focus on separating these guys. So I take these constants C1 and C2, I replace them with all of the x1s. So then I say C1, C2, A12, A22. And then I take the determinant of that guy. Okay, so I replace this with that column. And then I divide this by the determinant of these cofactors. What is it? It's this operator matrix. And then if I want to solve for x2, what do? I do the exact same thing. So now I focus on the column with the x's, and I replace the c's with the x2 terms. So then it reads A11, A21, then I get C1, C2, divided by like that. And that's the solution of this thing. But it turns out that this is inefficient by writing it like this. Technically, this is how you do it. Because you've got to take the inverse of this matrix and then put it into the denominator. But for us, how am I going to write this? I'm not going to write it like this. I'm going to immediately call this D. I'm going to do the algebra. I'm going to write D equal to x1 equal to C1, C2, A12, A22. And then I'm going to do dx2 is then going to be A11, A21, C1, C2. So it looks like this. Yes?
Why can I not row reduce the first matrix you set up? They're variable in the elements.
This guy right here?
Yeah.
Yeah, there's variables. In fact, what I was just about to say here is that the second order equation is contained in EF. And another thing that we're seeing once again here is that, look at that, x1 and x2. What's the difference between x1 and x2? It's not the d's, they're the same. What's contained in those d's? It's the so-called natural response, right there. It's the exact same thing. And so now what we can do here is that we can go in and we can then just go in and solve, and you'll see that this d here will have our differential equation that we're looking for. Now what's tricky here is that if on this side you'll get this s hat, inverse, then you'll see that we'll have to play a different game. And the algebra is a little bit tricky the first time you see that. But once you see it once, you'll see that it'll be okay. Okay, so what I was thinking about doing this is that I wanted to do one example using this Cramer method. And then I'm just going to try to move very fluidly as best as I can through this to try to show you that in the way I try to think of it is sort of like a rhythm. You got to get that rhythm. And as you move through this rhythm, there's these series of steps that we want to apply right here. So what are we going to do? We're going to try to do the following. We're going to try to do 1, 2, 3 steps all in one swoop. Okay, so we go all the way to here, and then we pause, we take the determinant, and then you'll see the differential equation pops out. Okay, let me erase and let's do an example. So this example is not an example that you have in your notes or your example sheet. Can I erase it? Anybody? Okay, so let's see if I can take this Okay, let's do it. So what I want to do here is that I want to do this example. So this will be essentially our third example. And why I'm going to do 4 examples. It's like super important. And then, as we get towards the end of the chapter, you'll see that we'll go from start to finish. Okay? So I need to do these examples as much as I possibly can. So here we go. So here's a fairly straightforward circuit. So they're all in parallel. So this is not a real circuit. Why is it not a real circuit? Because these numbers are too nice. They just don't happen. So what we want to look for here is we want to solve for the current of the inductor. So we're looking for IL of T. Okay, so we want to use Cramer's method to solve for IL of T. So here we go. Let's do this. So then I want to do steps 1.1, 1.2, 1.3 together. Okay? I want to do them all simultaneously. So the way I'm going to look at it, I'm going to do what? I'm going to set x1 to VC, x2 to IL. That's what we're solving for right there. Once I do that, I got to do what? I got to apply KCL to relate IL and IC. So then I'm going to go KCL, and then that means here that I got to relate that current and this current. So if I look at this current, you can see that the current is going to go down. So now I keep going. So I go, these two currents must be related according to KCL to this whole node right here. Right? So if I look at this, I could make this my node. All of the currents flowing into this node must flow out. I know there's a current to the resistor, and then I got these two currents. So then I write IS equals IL, IC, I1 ohm. And then I say, how do I replace these things? I got IL, IC I got to replace, and then I got to replace the 1 ohm resistor here. So here we go. So then I go IL plus what? CS hat. I'm sorry. Since we're talking about these numbers are nice, I'm just going to use that number 1/2. So I'm going to write 1/2 S hat VC. And then I look at this resistor here, and I see that this resistor, there's only one variable, right? One node, VC. I could have picked VL, that would have been totally fine, but I'm going to pick VC. So if I pick VC, you can see that the voltage of that guy should then be what? VC divided by 1. So I look at this equation and I say I got IL, VC, VC, I got everything in those primitive terms. So therefore, I source, this is my first equation right here. Now I'm going to do the exact same thing for KVL. So KVL says what? I got to relate the voltages of these two guys. Since these guys are in parallel, that means I'm going to write VC equals to VL. This is in terms of VC. This is the guy I got to rewrite. So as I rewrite this guy, I'm going to write this as what? L. L is 1. So then this will become 1 times S hat IL. So now I got them in these terms right here. So if we were looking for the initial conditions, what equation is going to help me? The derivative of the x2 terms. So the derivative of the inductor is this guy is that. That's equation 2. And that's for like step down with initial conditions. Yes?
For your KCL, the boxed equation you have, the V of C over something, what is that?
1 ohm?
Oh, I'm sorry, and your boxed equation? Oh, it's 1 ohm.
It's
Thank
1
you.
ohm.
Appreciate it.
I'm just doing that to remind you that there's a term. So now, we've done steps 1 through 3. So what am I going to do? I'm going to go in and set up my matrix. So then I'm going to go to step 1-4, and I'm going to set up the matrix and derive second order equation. So now I'm just going to treat this as 2 variables. What are my variables? VC and IL. Okay, so you can put them any way you want. The fact that IL is by itself here, I'm going to make that the first one. So let's go write this here. So I'm going to get IL, and you see these 2 terms, I can combine them. So when I combine them, look at these 2 terms here. There's my 2 VC terms right there. So if I combine them, it looks like what? It's got to be 1 plus 1/2 S hat VC IS. So there, I set it up with IL and VC. Now I'm going to do the exact same thing with this one. I'm going to subtract this to the other side. I'm going to bring VC to this side. So then I'm going to get S hat IL minus VC equals 0. And you can see now that I have it in matrix form. So if I put this into matrix form here, so now I'm going to put it into a matrix, and you can see that the ILs have to be what? 1, S hat. I look at the VCs, and it's got to be 1 plus 1/2 S hat, and then I get minus 1. So now I got IL, VC, IS, 0. So now I want to solve this equation using determinants, Cramer's method. Now we solve for IL using determinants. So let's do that then. So the thing that you want to pay attention here is that this term right here is my D hat term. Okay? What you want to pay attention to is the term on the right side of the equal sign. Okay? So here we go. So I'm going to go D hat IL. Okay? Now, here's where people screw up here now. What you want to do here is that, look at my IL terms. They're this column right here. So what do? I take this guy and I replace it with this column right here. So then on this other side here, I'm going to write IS 0. And then I have the rest of my term right here. So look how I created that right side now. Okay? So now if I take the determinant of this thing here, you can see that this term is going to give me what? Minus IS times 0. So then I'm going to get minus IS plus 0. So I know the right side completely. So now, what's left here is I got to take the determinant of D now. Okay? How do I take the determinant of D? I go 1 times minus 1. So then I get minus 1. And then look, there's a minus sign here. When I cross over, so then I get minus S hat, 1 plus 1/2 S hat. And this is all operating on IL. And this is equal to minus IS. So if I do that, the thing that I'm going to do now is I'm going to get rid of all these minus signs. Okay? And then I'm going to multiply this term out. So look at that. I got S hat on that S hat, so I'm going to get what? I'm going to get, so first thing I'm going to do here is look what I'm going to do. I'm going to get rid of all the minus signs. I got nothing. So now I'm going to multiply S hat times this 1/2 term, so I'm going to get 1/2 S hat squared. Then I'm going to multiply that by 1, S hat, plus 1, IL. So now what am I going to do? I'm going to convert that into derivatives now. If I convert that into derivatives, this is 1/2 IL dt squared plus di dt plus IL equals IS. And that's the second order differential equation right there.